Okay, hello everyone. I guess you probably know me. I'm Ian. So first of all, I will be your tutor for your unit FIT3155 Advanced Algorithms and Data Structures. So an important note is number one, I'm not your lecturer, so I will not be performing a lecture, right? You have a lot of resources from your chief examiner. Your lectures are recorded on Echo 360 or Moodle, which you can access it. Okay, but from time to time, I will actually provide a revision of an algorithm which you have learned from your lectures, right? Most of your tutorial questions actually begin with a revision of what you have learned in the lectures of the week before, right? And hopefully I will be able to clear up some of your doubts, some of your concerns, blah blah blah. Okay, so our first video is going to be on Garfield Z algorithm. So I've already set up our recording in a way where it will be mirroring me, left, right, working fine. And we will be making use of our whiteboard quite a lot. Okay, which is the only way I can figure out to really explain concepts through visualization easily, right? Because most importantly, you want to see me going through it step by step instead of me just showing slides with the output and explaining. Okay, so it's going to be about Z algorithm. Okay, your Z algorithm is, if you were to ask me, is your most important algorithm for your entire unit, because you're going to learn it in week 1. It's going to be applied in week 2 for your polymer. Your GMP also utilizes concept for it, and the whole entire mindset behind Z algo is used in many other algorithms as well. Okay, what is the motivation for your Z algorithm? If I were to provide you with a pattern, let's say A, B, okay, then I will to provide you with a swing, let's say A, B, 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 A, B, A, right? You have a very long swing given a pattern. Usually, your pattern should be shorter. So let's say here you have m number of characters. Your swing is usually longer and you have n number of characters. In the most naive implementation of all, you're going to be aligning your pattern with your entire swing. So 1, 2, 3, 4, 5, 6, m equals to 6, 1, 2, 3, 4, 5, 6, right? Here is where my alignment is 1, 2, 3, 4, 5, 6. Okay, and then what you're going to do is you're going to be comparing characters by characters to see if they are the same. Once you reach a given characters, you know it's not your pattern itself because I found a mismatch. Then you're going to perform a shift by 1 and perform the same comparison operation again, which is relatively expensive. From the mindset of a complexity, it's going to be O of n, right? Because no matter what, you need to compare all of the characters in the swing, and then you're going to have an additional n number of comparison, right? When you're comparing your patterns. For example, if my swing is all A's, I will compare from m equals to 1 all the way up to I will compare from the first character all the way up to the m character, right? To only realize the last character is not the same, shift by 1 and repeat the process, comparing the front characters n number of times, which is O of n. Very inefficient. So someone actually came up with, is someone which is Garfield, came up with the Z algorithm. Okay, what if we can put the pattern to be the front, okay, and then we can put the swing to be at the back, right? So I'm going to have A, B. For example, let's keep it shorter. Then I can have whatever string I want. And the goal is, if I can find a substring here which matches the prefix, right? For example, if I were to combine it into a singular string, if I can find a substring here which matches my prefix, means my pattern exists. If the length of my pattern m is equals to 5, if I am able to know the number here is 5, right? Or if I'm able to know if the 5 characters here is the same, right? Means both strings are the same. Okay, so your entire Z algorithm revolves around a concept called the Z array, right? Which is the entire processing or entire output of your algorithm. Okay, you're going to define a function called Z algo, which accepts in a string, right? If you notice, I only say string and not pattern, right? Because my string can be pattern called a string or whatever it is. I'm keeping it as modular as possible. You will understand why when you move on to your Poemon and KMP as well. Okay, then it's going to return a Z array. So I'm going to define my Z array, right? Could be an array from 1 all the way up to n, right? Where it is the same size as the one above. Clear so far? Okay, so how does your Z array actually work, right? So I'm going to assume I've gone through your lectures. Imagine I have a string. Let's put A, B, B, A, B, C. Okay, so for the purpose of easy observation, I'm going to assign numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? The numbers corresponds to the index or the position. Okay, why am I beginning it from 1? Because it's consistent with your lecture slides. And if I begin it from 0, you can just program it, right? And if you really see or test your understanding of the concept to see if you're able to program it with an index of 0, because Python begins from 0, right? Whereas all of our explanation will begin from 1. Okay, so let's call this the index. Okay, then I'm going to use black for the Z array. Okay, so my Z array is going to be a value for every position which I have. Okay, now what I save inside my Z array is the length of my substring, which is the same as the prefix. So for example, let's call my position here K, right? My Z of K, okay, if my set of K is, let's say M, okay, what I know is my string from the first letter all the way up to the M letter is going to be the same as the string from the K letter all the way up to my K plus M minus 1 letter, right? They are going to be the same. So in my example here, my K is going to be 5. Why is my K 5? Because if I load 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? You're going to realize my characters are the same. AA, BB, AA, BB. Right? Perfect. Okay, and then the next character, right, at m plus 1 will not be the same as the character of k plus m. Right, so over here you're going to see the sixth character, right? B and C is not the same. Okay, so what you see here is going to be your it's going to be the explanation of the numbers inside your Z array, right? Note, I'm talking about Z array, not the Z box. Please do not be confused, right? Z array is your output. Okay, so with that said, let me just erase everything again. Okay, and please provide me with a feedback if my okay, please provide me with a feedback if my explanation or my production can be improved, right? No promises because my surface is like 5 years old and it overeats at the moment. Only 4 gigabytes of RAM. Yep, I could accept donation if you wish. Okay, jokes aside. Now let us try to fill up our numbers one by one. Okay, our first number, right, or the Z1 will always be the same as the length of the entire string. Because if you care about it, you're comparing a character with the same character, which is always a match. Okay, you're comparing with the next character with the next character, which is here a match. So here my number is going to be 12. And because of that, the first number is usually not important, right? It's totally not important. We will usually ignore it, but occasionally, since we have allocated memory, might as well just save something, right? Which is the length of the list, which is 12. Next, we try to figure out what is our second value, Z2. So you're going to be comparing string at 1 versus string at 2. If it is a match, you're going to compare string at 2 with string at 3. If it is a match, you're going to be comparing string at 3 with string at 4. So here, in the first step, I compare A and A. Both alphabet is a match, so I'm going to put a 1. Okay. Then I'm going to increment my pointer, now comparing the second level, A and B. Is it the same? It is not the same. So my number is going to stop at 1. Okay. As a friendly reminder, I'm just filling up the Z array. I'm not using the Z algorithm yet. That's why there's no Z box. Next, I'm going to know what is the value in the third position. So I'm comparing Z1. No, my bad. I'm comparing string 1 with string 3, right? So A versus B. Is it the same alphabet? It's not the same. No match means the length will be 0. Right? Next, I'm comparing with 4. A and A is the same. Then I compare the next one, which is 2 and 5. A and B, is it the same? No, means only one letter which is the same. Right? Then I'm going to fill up the next position again. Here it's going to be 5. Right? A versus B is not the same. Move over to 6. A versus B is not the same. Look at 7. A and A is the same. Next set, A and A is the same. Okay, next set, A and B is the same. Next set, A and A is the same. Next set, A and B is the same. Next set, B and C is not the same. So 5 letters are the same. I will put the number 5. Okay. And then I'm going to fill up the next number, right? Increase equal 8 and 1. And just fill up all the way, right? This is how you fill up your Z array with a brute force. And you're going to find out an issue here. You're actually doing O(n) square number of comparisons. Because if you were to think about it, when I fill up the number 5, right? If you remember, I was comparing here, then I was comparing here, until I meet the last letter which is not the same, right? When I increment to compare the 8 character, right? Comparing the 8 character, you realize I'm comparing the character at position 8 again. In the worst case, I'm going to have string which is A, all the way up to the last letter which is a B. And you're going to realize I'm repeating my comparison over and over, which gives us O(n) square complexity, which is the same as our naive pattern matching implementation. So it's still a quadratic implementation which is totally not fast, right? We are repeating computations, we are redoing comparisons over and over. And you should have learned by now, since you're in 3155, from FIT3155, you have a very important concept known as dynamic programming, right? In computer science, always learn to be lazy, right? Least amount of effort, we use what you already have. So the Z algorithm is in fact a dynamic programming algorithm. There's no way around it. Okay? The trick is you're trying to reuse the pre-computed numbers from your Z array to figure out what is the new number. Okay? I repeat, Z algorithm is a dynamic programming algorithm. You're trying to reuse the pre-computed Z array values, okay, the previous Z array values to calculate the current Z array values. Okay, so view your Z array as a form of memorization, right? It's just dynamic programming. Okay, so if you have understood the motivation behind the algorithm, let me provide you with a little bit of definition which you need to know, right, before I move on to the Z algorithm. Okay, given a string, right, from the first letter all the way up to the n letter, okay, I'm going to define a Z box over here. Okay, your Z box will begin at position L. Okay, so we'll begin at position L and we'll end at position R, which is the left and the right of the Z box. Okay, what is the meaning of Z box? Okay, whatever number which I'm saving here, right, let's put it ZL. Okay, whatever number which I'm saving here is actually R minus L plus 1. If I want to include R, if I use R as the outside of my box, it really depends on your own implementation. So I'm going to explain the concepts, and my explanation will have a plus minus 1 difference from implementation. Okay, so ZL will save the value of R minus L plus 1 if I have a Z box from L to R, right? And I know the number here, right? And I know the number here actually denotes every letter here from L to R is the same as every letter here, right? Which is L, which is L, R minus L plus 1. Okay, the size of your Z box will always be the same as the size of the C box at the front, right? They are always a mirror. Yang be different, right? So if my R becomes bigger, L will also become bigger. If my L becomes bigger, it will be smaller, blah blah. Okay, so what it also means is my alphabet's L is going to be the same as my alphabet's L. Okay, the characters in both Z box are exactly the same. Okay, so far? Nice. So, if you understand what is a Z box, I need to draw it again. Okay, let's draw a Z box here. This will be L, this will be R, which corresponds to L. Okay, let's assume I'm going to fill in my value over L. Let's put it at I. Right? So I'm trying to compute Z I. I do not know what the number is. Everything else to the left, I've already computed it before. Remember, it's dynamic programming. My entire array on the left hand side have already been filled up. I just want to know what is the number at position I, right? Because I need to fill up my number from left to right. Okay. So I'm going to just write another field notation. Okay. Minus L. I'm going to use my R as the boundary because I'm very lazy to include a minus 1. Okay. Now, I'm going to put another definition. Let me use a different color. For example, let me use blue. Okay. I'm going to define here as the remaining. Okay, I'm going to define here as remaining. And you're going to realize my remaining is the same as the one here. Okay, I can spell remaining always. Okay, and I'm going to have something over here which is equivalent. Let's call it K. So if I were to add in more values, remaining, give me a moment. Okay, remaining equals to R minus I. Okay, and then K, right, which is on the left side, will be R minus L minus I. Okay, so K will be the equivalent or the mirror of I. Okay, is this part clear so far? Okay, so where is the dynamic programming part? The dynamic programming part actually lies here. ZK, okay, can actually be used for you to find out what is ZI, right, without having a lot of recomputation. So this is the entire essence of your Z algorithm. Okay, and remember, if I were to bring in my remember if we were to bring in our previous observation, the alphabet here, the one I marked in red, is not the same, right? Here and here will be not same. Okay, and whatever I'm drawing you here is something which you should probably see in your exam as well, right? Because a lot of your exam question about Z algorithm is reliant on a visualization of what your Z algorithm is from the perspective of a very long string and of the Z box on the string itself. Okay. Once I've defined all of my diagram here, your Z algorithm is just a very simple if-else algorithm, nothing else. Okay, it relies on case 1, case 2. Okay, case 1 actually occur when when I is outside the box. Outside box. Okay, what do I mean when I say I is outside the box? So in my example here, imagine my I itself is actually outside my box. Because I is outside my box, I do not have an equivalent box on the left. Because I do not have an equivalent box on the left, I do not have prior computation, I do not have any memorization for me to use. So when case 1 occurs, you have no choice but to perform all of the comparisons in the world. Right? No dynamic programming will be possible. Case 2 is when dynamic programming is possible. I know your lecture slides only have 2 case 2, A and B. Here I'm going to show you 3 cases, A, B and C, because it's part of your tutorials, it's examinable, and you're expected to implement it for all of your Z algorithms, including the one being assessed in your assignment. Okay, so case 2A is going to occur when Zk is less than the remaining. What it means is the number here, Ck, right, is going to be a number which is smaller than my remaining, which is my R minus I, right? Which means whatever number which I save in my Z box, okay, is less than my remaining itself. So if I were to give you an example, okay, if I have a Z box like the following, let's say this is I and this is K. Let's say my remaining have a size of 10. And if I look at the Zk, the number which I'm saving here is only 4. Right? Means the 4 alphabets here is the same as my prefix. That's all. Right? So this is the first case. The second case is when Zk greater than remaining. Okay, so in the same example, the number which I save is longer. So for example, if my remaining have a size of 10 and the number here which I save as Zk is 11, right? Means 11 character from K onwards is the same as my prefix. Okay, and the last and final case will be Ck equals to remaining. Here so far? Okay, I'm going to use all of the definition of my cases here. I'm going to work on a real world. Not really a real world. I'm going to work on an example now. Okay, and we are going to build the Z box together. Let's begin with the string, right? Then we are going to have the index, which is just to make our life easier. And then we are going to have a Z array. So my string is going to be A, B, A, B, C, A, X. Wait, first A, B, C, A, X, A, B, oops. Okay, AAB, CAX, AAB, CY. Okay, so let me just put on the index quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right? And I will draw out a boundary box so we can see it so much easier. Okay, pardon my drawing. I have issue drawing straight lines. Okay, I think this is a little bit. Okay, yeah. Whew. Okay, I need to have a drink. Okay, so we are now going to try to fill up the Z box. We are going to try to fill up the Z array using the Z algorithm. Okay. First of all, as we know, the first position is totally not important. We usually ignore it, or we usually save the length of the entire string, which is 17. Clear so far? Now, we could not have a Z box. What happens if we could not have a Z box? If we could not have a Z box, we go into case number 1, right? So my I is over here. Okay, my I is over here, and I could not have a Z box. So no Z box in dynamic programming, no memorization which is usable. I have no choice but to compare my alphabet, right? So string of 1 versus string of I, right? A and A is the same, right? Which is okay. Then string of 2 versus I plus 1. B and A is not the same. So I'm going to put a number 1 here. Clear so far? Okay. So because I put a number 1, okay, I now have a Z box. Okay, my surface is overeating very badly and it's not recognizing my pen. Okay, I'm going to pause the video for a moment. Okay, I'm back. Sorry, hardware failure always happens. Okay, so because the number is not a 0, I now have a Z box. Okay, and then I'm going to increment my I to the next position. Is my I within a Z box? No, my I is not within a Z box. So I'm going to go back to case number 1 and perform off the manual comparison. A and B is not the same, so it will be 0. No other comparison is needed. Increment my I. Because my number is 0, I could not have a Z box. My Z box still maintained at the previous position. And my I is here outside of my Z box. Because my I is outside of my Z box, no choice, manual computation. A and A is the same. A and A is the same. B and B is the same. C and A and C is not the same. So my number here is going to be 3. Okay? Because my number here is 3, right? It means I will now have a new Z box. And my Z box is going to be here. Right, a box of size 3. And what's the meaning? The 3 alphabets here, A, B, is the same as the prefix 3 alphabets, A, B. Right? And the 4th alphabet is not the same, which is A and C. Right? That's what your C box is. So increment my I to the next position. Now, once we reach the situation here, we already have a Z box, right? And because we already have a Z box, we are going to be able to use some form of memorization, some form of dynamic programming. So if you were to look back at my previous visualization over here, okay, if this is I, K will be here, right? So Zk equals to 1. What is my remaining? My remaining will be 2. Right? One alphabet at I, one alphabet at from after I all the way up to R. Right? So I got a remaining 2 boxes to fill up. And if Zk is 1 and my remaining is 2, it brings us to our case 2A, where Zk is less than remaining. When Zk is less than remaining, Zi equals to Zk. So here I can just instantly write the number to be 1. No comparison required. I do not even care if the alphabet exists. Not important. Right? You have just assumed the number of 1 is correct. But it's not an assumption. It is really correct. Let me explain why. Okay? Because you have the Z box, you know the alphabets here and the alphabets here are the same. Right? So if I've computed anything on the left hand side, I should be able to use it on the right hand side. My computation on the left hand side tells me that at position K, the substring beginning from position K, which is A, B, A or whatever, if I were to compare with the prefix of the string, only the first character is the same, which is why I have the number 1. But since my alphabet on the left hand side is the same as my alphabet on the right hand side, means what my previous computation of B, right, which I know is a given alphabet, right, because the number is only 1, from the prefix, but okay. Let me just put it out now. A, B, A, B. Okay. I have a Z box. Okay. Let me put a few number. Not important. 1, 0, 3. Okay. Because here I got a Z box here. Okay. Let's make a few observations. Number 1. Because the number is 3, I know the 3 alphabets of A, B is the same as my prefix A, B. This is a part you can agree. I also know that the 4th alphabet after is not the same. Okay? Because if the alphabet is the same, the number here should be 4 and not 3. Okay. Then, if we were to look at the number here, right, of Zk equals to 1, means the alphabet here is the same as my prefix, but the next alphabet, the second alphabet, right, because the number is only 1, the second alphabet is not the same as the prefix. Okay? But the alphabet here and the alphabet here is the same, which means, right, A and A is the same as the prefix, B and B is not the same as the prefix, but I've already previously computed B is not the same as the prefix. So I do not even need to look at my B anymore to know B is not the same as the prefix, and I can just reuse the number 1. Okay? To make sure you really understand, I'm going to repeat it for one last time. Okay? The number is denote the substring of A, B onwards. Only the first alphabet is the same as the prefix. The second alphabet is no longer the same as the prefix because the number is only 1. But since the left portion is the same as the right portion, means the substring from here is going to be somewhat similar as the one here, right? Because the alphabets are the same. And because the alphabets are the same, you know A and A is the same as the prefix. B and B is not the same as the prefix. So the length of 1, you can just reuse it instantly. Okay? So this is the first case, which is why you're able to just reuse it instantly. Okay. And let me just erase the part above again. Okay. And my new number is 1. For a number of 1, right, my 1 is here less than my remaining, so my z box doesn't change. Okay, so when I increment my I do not change my z box. Okay, so when my I increment, my k also increment. I realize set k is 0, my remaining is 1, therefore set I equals to set k equals to 0. Copy it. Because the number is 0, right, which is less than my remaining, I do not have a new z box, increment my I, right? And because I'm outside of the z box now, which is the same scenario as case 1, I do not have dynamic programming anymore. I need to recompute everything manually. A and C is not the same, so it'll be 0. It'll be 0. Increment my I. Okay. I is outside of the Z box. Case number 1, no choice but to repeat my computation. A and A is the same. A and X is not the same. So the number is 1, right? Because I'm no longer within the Z box and the number is greater than 0, I will now have a Z box of 1 and I'm going to increment my I. My I is here outside of the Z box, right? X is not the same, it will be 0. Increment my I. Outside the Z box, no choice but to recompute everything again. Okay, so A, right? A and A is the same. B, A and A is the same. B and B is the same. A and A is the same. A and A is the same. B and B is the same. Right? A, B, B. C and C is the same. A and Y is not the same. So 1, 2, 3, 4, 5, 6, 7. The number here is going to be 7. And because I have a number here, I'm now going to have a new Z box, which is of length 7. Okay, and my I is going to be here. Okay, so far? Good. Okay, so because I is now inside my Z box again, I'm going to come back to my previous scenario, right? A Z box actually exists. So I now have an equivalent Z box here. So the characters in my Z box are exactly the same, right? Because they have the number of 7. And because it's the same, I now reactivate my dynamic programming advantage of having a K. So at the moment, my remaining is actually 6. My set K is actually 1. Because 1 is less than 6, K is equal to A, I can instantly just put the number 1. No computation, no comparison required. Then increment my I to the following position. My K also increment, right? Remaining is now 5. set k is 0, just put the number 0. Right, increment my I again, which is the following. Okay, remaining becomes 4. K comes over here. 3. Set k is 3. 3 is less than 4. I can just put 3. If I'm going to double check, 3 because AAB is the same as AAB, and the next character of Z is not the same as the character A. Right? And you realize I know this by just comparing my values earlier. Right? It's just in your brain work out the logic, right? The concept of cohesivity, right? If Ian is my friend and Ian is bad, therefore my friend is bad, right? It's the same logic. Okay, so because I just copy, right, the new 3 is less than my remaining, so my old Z box will still maintain. Increment my I, increment my K, right, and my remaining is going to decrease. Now it becomes 3. ZK is 1, 1 less than 3, copy it. Okay, my I will now be here, right, remaining becomes 2. K will now be here 0, copy a 0, K, I, 0, and finally I will be 0. That's all. Right. So in the first example which I've given you over here, okay, you can see wherever I'm inside my Z box, I do not need to do any comparison. Okay, if I'm not inside a Z box, I need to do comparison, but my comparison will build a new Z box over the comparison, which I will ignore in the subsequent comparison. Therefore, my entire complexity can be summarized as O of N. Okay? Right? As a recap, if it's case 1, I need to perform comparison. If it's case 2A, I do not need to perform comparison because I have the box. Okay? But case 1 will generate a box, which means whatever which I compare as I generate a box, I do not need to recompute it again. Right? And if case 1 doesn't generate a box, I terminate, because if the alphabet is not the same, I just move to the next character and compare. So the entire process will give me a complexity of O of N, which is really nice, really fast and efficient. Okay, so hopefully you have understood case 1 and case 2A. Let us move on to case 2B and 2C. Okay, let us try with another example here. No, my bad. ABS, C, ABS. Okay. Put in numbers again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so let me just draw out the box. Okay, So let us begin the process. I'm going to go a little bit faster now, since I'm going to assume I have understood case 1 and case 2b. Okay, first position 19. Second one, compare A and A is the same, A and B is not the same, it will be 1. So now I will have a Z box here. But my I is outside my Z box, it will be 0, 0. Here will be 3, no, it's not 3. A and A is the same, A and A is the same, B and B is the same, X and X is the same, A and C is not the same. So it will be 1, 2, 3, 4, 5. No, 4. It's only a 4. Okay, so now I have a Z box of 4. Okay, because I have the Z box of 4, I know the 4 alphabets are the same, AABX, AABX. Now I want to know my I. What is my I? Because it's within a Z box, I also have a K. My remaining is going to be 3. So ZK equals to 1, remaining equals to 3. Case to A, I can just put the number 1, increment my I, and make my remaining smaller, increment my K, right, this becomes 2, this will be 0, increment my K, this will be 0, and then my I will be outside, it will be 0, I will be outside, and begin my computation again. Okay, A and A is the same, A and A is the same, B and B is the same, X and X is the same, same, different. So all the way up to 8. That's why my number here is going to be 8. Okay, then I'm going to build a Z box over here, right, which is the same as my Z box over here. Okay, next increment my I. My I will now be at the current position. Remaining will be 7. Okay, and my K will be here. Because it's smaller, it's going to be 1. I will be here. K will be here. 0, 0, right. Then here comes across the interesting part, which is the 1 here. Right, where my I is here, and my K will be here. Okay. This is a very, very interesting observation which you can make now. My remaining equals to 4. Okay, ZK equals to 4. What does it tell us? Okay, number 1, if ZK is equals to 4, it means the 4 alphabets here, AABX, is the same as the first 4 alphabet here, AABX. Right? And the next alphabet is not the same, because A and C is not the same. This part you agree. Okay? But because they belong in the same Z box, means my alphabet here is also AABX. Means from the number 4, I know at least the 4 alphabets are the same. But I do not know what is the 5th alphabet. Okay? What I know is the 5th, let me just call it blah 1. Let me call it, oops, sorry. Let me call this as blah 2. What I know is blah 1 is not the same as blah 2. Right? But what about blah 3? Right? What I know is blah 3 is not the same as blah 1. Why? Because if blah 3 and blah 1 is the same, the number over here should be 9. Right? Because it only goes up to 8 because the next alphabet, which is blah 1, is not the same as the alphabet here. So, since they are not the same, there is a chance, right? There is a chance, blah 2 is the same as blah 3, right? Blah 1 is not the same as blah 2, right? And let me just rewrite it. Let's change it to 1. Okay, blah 1 is not the same as blah 2. Blah 1 is not the same as blah 3. But can blah 2 be the same as blah 3? Maybe. Okay, so because of this observation, what happens if blah 3, okay, let me choose another, what happens if blah 3, oops, can I undo? No, I can't. Okay. What happens if blah 3 is the same as blah 2? If blah 3 is the same as blah 2, means I may have a new Z box, right? If blah 3 is the same as blah 2, it means my number over here will be greater than 4, right? Because it is possible for me to have a Z box which is bigger. Okay, so I'm going to start comparing from blah 3 onwards. You do not want to compare what is inside the box. I'm going to only compare from blah 3 onwards. A versus A. Is the alphabet the same? Yes. Y versus A. Is the alphabet the same? No. So my number here will be 5. Right. So Zi equals to 5. Okay. Let me repeat again. Okay. If Zk is the same as if Zk is the same as remaining. Okay. We know the string from K all the way up to from K up to L R minus L is the same as string from I all the way up to R. Okay, but we also know string at R minus L plus 1, the next letter, is not the same as string of R plus 1. Okay? This is from our Z box. Okay? But we also know C of K all the way up to remaining is also the same as the string of K all the way up to remaining is the same as string from position 1 all the way up to remaining. But there is a chance string of remaining plus 1 can be the same as string of r plus 1. Therefore, you want to compare all of your additional characters as what you can observe here, right? When you have a zk of 4, okay, it just means that the 4 letters here is the same as the prefix, okay? But since they belong in the same box, you also know the 4 letters here and the 4 letters here are the same, right? Which means our next letter of blah, right? Blah 1, blah 2, and blah 3. Blah 1 is not the same as blah 2. Blah 1 is not the same as blah 3. But there's a chance for blah 3 to be the same as blah 2, which means your number here can be greater than 4. So which is why you're going to need to compare after your Z box, right? And because the number here is 5, I will establish a new Z box 5. And my I is going to increment again and perform as normal. Okay, so this is case number 2C. Which leaves us with case number 2B. Okay, so let me just go back to the summary I've provided here. Okay, Zi equals to Zk. Okay, here will be compare string r plus 1 onwards. Okay, we are going to left with the final one, and I'm going to tell you the answer here is Zi equals to Zk. Are you able to reason out why? Okay, so let me just draw an example here. I have a Z box, I have my I have my L, I have my R. Okay, here will be my K. Okay, my remaining will be here. Okay, remaining here also will be my remaining. Okay, what I know is Zk greater than remaining. So what happens if Zk is greater than remaining? Okay, first thing first, because they are in the Z box, you know the characters in the box are the same. Okay, number 2, you know the next character outside of the box is not the same. Okay, what happens if when Zk is greater than remaining? It means that I have a substring outside of the from K to outside of the box, which is the same as the substring here, which is why the number is bigger. Okay, which makes sense, but it means my character over here, right? So here will be my remaining. Here will be my remaining. Okay, so if I were to color it over here, okay, it's going to be the same as the one here. Okay, but I know this character and this character is not the same. Because it is not the same, no matter how big is the number, you're only bounded by the remaining. So here, oops, my bad, my brain is blur. Here, it means my answer will be the same as remaining. Okay, so I've provided you with your Z algorithm and also the explanation of all the three cases, case 1, case 2, ABC, right? The most important part is always your case case Q A, Q B, and Q C. Any questions? Okay, let me try to explain case Q B again. Okay, let me try to explain case Q B. Given a string from 1 to n, I have Q Z box over here. Because I have Q Z box, I know the letters are the same, but I know the next letter is not the same, right? So let's use alphabet. Let's say this is A and this is B, right? You know the alphabet is not the same, because if the alphabet is the same, your Z box is going to be bigger. It will be R, it will be L. Then here will be my I, here will be my K. And here is where I define as my remaining. Likewise, here is where I define as my remaining. If the Z K is greater than remain, it means I have a portion here, okay, I will just color it, which is the same as the portion here. Right, because remember, every number is the length of the substring, which is the same as the prefix. But my letter over here, let me use red. My letter over here, which is alphabet A, will mean my letter here should also be alphabet A, right? Because they are the same, but it is different. So therefore, it will also be different from the prefix, which means my longest substring, which is the same as the prefix, will be bounded by my remaining. And because it's bounded by my remaining, right, my ZI will always be equivalent to my remaining. Okay, so your past year exams always would like to ask you one of the three cases based on a given diagram or an explanation. So this is the part which you need to really know, and it's also the part where I actually extend it beyond what is in your lecture sites. Your lecture sites only have case 1, case QA, and case QB. I get your case QB and separate it into QB and QC, right? And if you think I'm just being extra, I'm not being extra, because this is what Arun actually asked here in question number 3 of your tutorial. So your tutorials will be a recap of your lecture, okay, with additional information which you need to know, because it's not possible to fit everything inside your tutorial, and all responsibility is passed on to me. Yeah, so it's a really long explanation. I hope you understand it. Of course, if I were to visualize it face to face, it'll be much easier, because I can point what am I explaining, versus here I can't point, right? The whiteboard app doesn't have a laser pointer option, unfortunately. If I were to use OneNote, the machine is not powerful enough as well. So watch the video, try it out manually by hand, right? Come up with a few examples on your own. Any questions, please ask me, and I will go through the remaining of your tutorial question in subsequent videos to be uploaded. Thank you very much, and bye.